Day 50, conservation of momentum, problem number 13. Here we have a car that's going to hit a wall and come to rest. So we're going to use the relationship between impulse and momentum to figure out the average force on the car. And if you look here, the momentum equation, P equals mv, we can find the initial momentum of the car just by taking its initial velocity of 1,500 times its mass of 1,500 kilograms, make sure it's kilograms, times the speed in meters per second, 25 meters per second, and we get initial momentum of 37,500 kilograms meters per second. The car hits the wall, comes to rest, so its final momentum is 0. The key here is the change in momentum, which is simply the initial minus, or the final minus the initial. Technically, it's a negative change. We don't need to worry about the negative here. We'll talk about that later. So if we go to the relationship over here, that J, which stands for impulse, is equal to change in momentum, and impulse, right, is average force times time. So we take the average force times the time and plug that in for for impulse, equal to the change in momentum. Then what you'll do is plug in for the time of 0.12 seconds and solve for the average force exerted on the car during this crash. And additionally, once again, momentum is conserved. We didn't really apply that principle directly, but the individual car's momentum wasn't conserved. The car lost momentum, but it was transferred to the concrete abutment, although really what is transferred to is the earth, because that abutment or that wall is attached to the earth. The earth and wall system is an object kind of all stuck together. So momentum is conserved. It'd be hard to show you that the velocity of the earth somehow gained a little bit from the crash, because it would be inconsequential, but momentum still was conserved.